Hello student, the question says three concentric spherical shells have radii A, comma, B and C and have surface charge density sigma minus sigma and sigma respectively. If A, VB and VC denote the potentials of the three shells, then for C equal to A plus B, what is the respective conditions we have to tell? Before we solve this problem, let us look at the formulas of a shell. For a shell, potential inside, this entire thing inside this is empty, and if Q is the charge of the shell and R is the radius of this and sigma is the surface charge density, let us see the formulas. Whether you take inside, whether you take surface, both have same formula, which would be equals to KQ by R. Why both of them have same formula? Right now I won't get into the derivation part. So it is, you should know this formula, 1 by 4 pi epsilon naught Q by R. The same thing, if you want in terms of surface charge density, we can write Q equals to surface charge density into surface area, 4 pi r square divided by r. So if you solve this, you will get V inside equals to sigma by epsilon naught into r. Rather than mugging it, you should mug this term, kq by r. You should be able to quickly get to this expression. Then let us see what is the formula outside, any point outside this. If you take any random point, this entire inside, any point inside this shell would have this formula. But if you go outside, even on surface also it's okay. But if you go outside, the formula would change. And now let us see what is the formula for outside. V outside would be K Q by, let us say from here, from the center, this distance is X. So KQ by X. So we can write this as 1 by 4 pi epsilon naught. Q can be written as sigma into 4 pi r square divided by X. So for any point outside the shell, the potential at that point is sigma by epsilon naught into r square by x. So these are the two important formulas we are going to use. Sigma by epsilon naught is common. For inside it will be r, for outside it would be r square by x. Now in the given question, we have three shells, A, B, C. Let me call this as shell 1. The inside, most inside shell, I will call this as shell 1. This shell, I will call it as shell 2. And this outside shell, I will call it as shell 3. So right now we have three shells, shell 1, shell 2, shell 3. The radius are A, B, C. And when the author says, if VA, VB, VC denote the potentials of the three shells, it means that potentials on the surface of the three shells. So let me select 3 points on three surfaces. Let me select this point first and call this E. I want potential at this point. Don't get confused between point A and radius A. This point A is just some random point on the surface of this shell. Now let us find potential at A. If you want potential at A, you should, potential is a scalar quantity. So you first, whenever you need to find potential at a location, you have to find what are the number of charged bodies in a problem. There are three charged bodies. First shell 1 with surface charge density plus sigma. There is another shell 2 with surface charge density minus sigma. Another shell 3 with surface charge density plus sigma. So we have three shells plus sigma, minus sigma, and plus sigma. So we have three charged bodies. Since there are three charged bodies, each charged body would contribute for potential at this location. That means V at A is simply V due to shell 1 plus potential due to shell 2 plus potential due to shell 3. So all these three shells together would contribute for potentiality. Now, before we solve this problem, first you have to identify for this shell 1, for this shell that we are selecting, this is my shell. For this shell, is this point A inside or outside? This point A. So the point A is for the shell 1, it is on the shell, on the surface. Next, for point 2, for shell 2, okay, now select this shell 2. So this is my, This is my shell 2. For the shell 2, where is this point located? For the shell 2, if you can see, this point is located inside the shell 2. So if you need to select it, this is my shell 3, and whatever is inside is the shell 2. This point A is located inside the shell 2. Since it is located inside the shell 2, so for shell 2, this point is inside. Then for shell 3, this outer layer is called shell 3. Where is this point A located? This point A is located inside. So this A is here, but the shell 3 surface is here. So this point is located inside this. Since it is located inside, so for this also I can write inside. Once we write this, simply substitute in the formula on the surface. We know on the surface or whether it is inside, the formula is sigma, its surface charge density, plus sigma due to shell 1 by epsilon naught into r. What is the radius of this? It is A. Then for the second shell, this point A is inside. What's the formula is sigma, so minus sigma by epsilon naught into what is the radius of the shell 2? The radius of the shell 2 is B. Then for shell 3, again plus sigma by epsilon naught into radius of the shell 3 is C. So finally, if I get sigma by epsilon naught common, you got A minus B plus C. So this is the final expression that we got here. A minus B plus C. This is the potential at A. Now let us try to find the potential at some other point. That is point B. So the same question now, right now we are interested in finding potential at another point, not at this location, but rather we want potential at another location. Let me call this point as point B. Don't be confused with radius B and point B. So this is the point B. Similar, if you want potential at point B, so we have again three shells due to shell 1, potential due to shell 2, plus potential due to shell 3. So first let us see shell 1. If I start from the center and go to this point, this is we are crossing the shell 1 and reaching this point. That means this point B is outside the shell. So first we have to write this. This point B is outside the shell 1. Where is this point B located? This point B is located on the shell 1, shell 2. It is located on the shell 2. So we can write on the surface. Then what about V3? This point B is the shell 3. You can see it is located inside the shell 3. Like still we did not reach the surface of the shell 3. It is this point B is inside the shell 3 only. So it is inside. Once we got this, we will use the respective formula. For outside, as you remember, the formula is not sigma by epsilon naught into r, it by sigma by epsilon naught into r square by x. So sigma by epsilon naught into r square, radius of that a square. X is the distance from the center to the point. What is the distance from the center to this point? You can clearly see that is nothing but B. Because if this is B, this is also B. So this is B for the first shell. For the second shell, since it is on the surface, it is minus surface charge density minus sigma epsilon naught into radius of the shell. The radius of the shell is B only. I have written that. Then plus sigma by epsilon naught into the, since it is in shell inside, so radius of the shell C. So if I get sigma by epsilon naught common here, I will get A square by B minus B plus C. So this is the next expression that we got. Now let us try to go for the last expression, that is potential at shell C. So if I try to find what is the potential at this location, let me select the last point here. So this is the point C. If you want potential at C, Again, what are the three shells that are contributing? Potential due to shell 1 plus potential due to shell 2 plus potential due to shell 3. Now, where is this point C located? For the first shell, for the first shell, to reach point C, we have to go beyond the surface of the shell 1. So, for the first shell, this point C is located outside. Where is this point C located for shell 2? For shell 2 also, we can clearly see to reach this from the center of the shell 2. For all of them, if you notice, they have same center only. That's what the meaning of concentric shells. So when we keep on traveling, we have to cross the surface of the shell 2. So this is also outside. For the last one, you can see this point C is located on the surface of the shell 3. So on the surface. Now use the formula accordingly. The formula is sigma by epsilon naught into r square by x. So sigma by epsilon naught into r square by, what is the distance of this point from the center of the shell 1? From the center of the shell 1, not from the surface. Everything is measured from the center. It is nothing but c. This distance is c. So by c. R is nothing but a. So a square by c. Then plus, we have minus sigma by epsilon naught. Radius is b square, distance is c. For the shell 2 also, radius is b square, but what is the distance? This distance from the center is, for the shell 2 also, it is c only. The next one is sigma by epsilon naught into, this is on the surface, c. So if I get sigma by epsilon naught common, I'm getting a square minus b square by c plus c. We can write a square minus b square as a plus b into a minus b. So if I substitute it, I'll get sigma by epsilon naught into a plus b into a minus b divided by c plus c. But in the question, it is clearly given that c equal to a plus b. That's the condition given in the question. It is given c equals to a plus b. Since c is equals to a plus b, since c is equals to a plus b, first I can cancel this a plus b and c because c is equals to a plus b. So I'll get sigma by epsilon naught. Since c and a plus b both are same, I will cancel them. So sigma by epsilon naught, what is left? A minus b plus c. So we have sigma by epsilon naught a minus b plus. If you notice that we got this conclusion somewhere earlier, where is that we got this conclusion? It is nothing but VA only. So finally, we got VA is equals to VC, which is sigma by epsilon naught A minus B plus C. And VB only we got some unique value, sigma by epsilon naught A square by B minus B plus C. But if I still want to substitute and do it, like let us say if you are like I simplify this further, we'll get A square minus B square by B plus C. So we can write sigma by epsilon naught A plus B into A minus B. So we will get C by B into A minus B. Even this is not like that much significant. If you want to simplify it, you can further simplify it in this way. So this is how we get the expression, and we can write sigma by epsilon naught. If I get C outside, we will get A minus B plus B by B. So we get sigma by epsilon naught AC by B. So this could be an expression on solving this. So finally, we can conclude that VA is equals to VC, which is not equals to VB. The correct answer for this problem would be VA equals to VB. VA equals to VC, which is not equal to VB. So the correct answer for this would be option D. But remember, this question itself is important. The question is repeated in many competitive examinations in different way. He could give another question. He could give the same question. This time he can give you condition. He can give if VC is equals to VA, find relation between CAB. In this case, the answer would be C equal to A plus B. So remember this question, like this is one of like important models in the competitive examinations. Either he can give you this condition and he can ask you to find the relation VC equals to VA, or he can give VC equals to VA and you must comment on this condition. But the most important thing is you should know what's the formula for inside and outside, both of them sigma by epsilon naught. This is directly into R. This is R square by X first thing. Next thing, whenever you select a point, don't be confused between point A and radius A. If you select a point, all the three shells would contribute for the potential at that point. How do you find the contribution of each shell? That is simply by scalar addition. When you have VA, simply contribution of shell 1 plus contribution of shell 2 plus but this itself is also not straightforward. When you try to find contribution of shell 1, you should identify whether this point A is inside the shell 1. Is it in? Suppose this point A, is it inside the shell 1 or is it outside the shell 1 or is it somewhere else in the shell 1? So that is something, is this point A inside or on the surface or outside the shell 1 or on the shell 2 or inside the shell 3 or on the shell 3? You should be able to identify the location of this point very clearly. Once you are able to identify the location of the point very clearly, rest is formula substitution. We have done for all three. But the speciality is that in the three, if you simplify it, you will get that this VA is equals to VC equals to VB. Hope you understood how I have solved. Thank you.